Okay, now we're going to relate the concept of isomorphism to the idea of dimension. Remember, we introduced dimension as the number of vectors in a basis of the vector space. And we've seen that dimension is a very deep property of a vector space in the sense that any basis of a vector space has the same number of vectors in it, which is equal to the dimension. So dimension is a very characteristic property of vector space. And in fact, we're going to show that any two vector spaces that have the same dimension are isomorphic. That means as far as vector spaces go, I should say as far as vector space behavior goes, dimension really tells you all you need to know about vector space behavior. Okay. So let's continue. First, we'll prove something I've been talking about, that the inverse of an isomorphism is also an isomorphism. What that means is that V is isomorphic to W if and only if W is isomorphic to V. Now, we've been a little bit sloppy about that. When we've established an isomorphism, we've said that the two spaces are isomorphic. But this proof shows that, in fact, it's a two-way street. If one vector space is isomorphic to another vector space, then that second vector space is also isomorphic to the first vector space. Okay, so let's go ahead with this proof. Suppose that V is isomorphic to W. So we just draw a map here. Here's V and here's W. And we have a map here, F. Remember, this map F is one-to-one and onto and preserves the operation. Now, in order to show that W is isomorphic to V, we need to get a mapping the other way that's also an isomorphism. And what we're going to show is that F inverse exists, and F inverse is also an isomorphism. Okay. All right, now, we start by realizing that an isomorphism is a correspondence between the sets. Another word that people often use is bijection. Okay, so an isomorphism is a bijection. So F has an inverse function that's also a bijection. Okay, if you're not familiar with that fact, you can go back to your discrete math textbook, or you can look up bijection and see this property that a bijection has an inverse that's also a bijection. Now, we'll show that because F preserves linear combinations, then F inverse does also. Okay, so let's take any two vectors in W. Remember, our map looks like this, V and W. And F inverse goes from W to V. Now, we've already shown that F preserves structure, and we want to show now that F inverse preserves structure. So we're taking two elements in here, and we're going to form a linear combination of those two elements and show that F of the linear combination is the linear combination of the images. Okay, so take W1 and W2 here. Because F is an isomorphism, F is onto, which means that there are vectors in here, V1 and V2, that map to W1 and W2. So we can write W1 is equal to F of V1 for some V1, and W2 equals F of V2 for some V2. Now, we're trying to show F inverse is an isomorphism, so let's take F inverse of this linear combination of W1 and W2. Okay. I'm going to write W1 as F of V1 and W2 as F of V2. Okay. Now, by the isomorphism property of F, I can combine these two terms and put the linear combination inside. Right? So I can rewrite what's inside these parentheses as F of a linear combination of vectors in V. At this point, I can use the definition of inverse to say that F inverse of F of any vector is the vector itself. Now finally, since I'm trying to prove something about F inverse applied to W's, F inverse applied to these W's, I want to rewrite this expression in terms of W's. But I remember that V1 is F of W1. W1 is F of V1. That's the same thing as saying F inverse of W1 is equal to V1. And this is the same thing as saying F inverse of W2 is the same as V2. All right, so I can rewrite this expression with V's in terms of W's, and I get my result. Okay. This seems like a lot of flipping around with V's and W's. The point is that we know that we want to get an expression like this, and we want to break it apart as a linear combination of the individual F's. And in order to do that, we need to re-express the W's in V language because we've proven our isomorphism properties with the F's and the V's. So that's exactly what we've done. We've translated the W's into V language. We've done our isomorphic manipulations with the V's. We've done this combination here. Then once we've done that, we need to translate back into W language. Okay. There are many mathematical arguments like this, and I think the more you see, the more you'll understand how this is a typical mathematical argument. Okay, so the upshot is that we have shown the isomorphism statement, or I should say the structure-preserving statement for the map F inverse acting on vectors in W. All right, so let's look at an example. If I take this line L in R2, remember the line that we had here, it looks like this, and it certainly looks like R1. Okay. And so we want to show the inverse mapping is also an isomorphism. Okay, so let's go to this mapping. It says F of T and 2T maps to T. So it's pretty clear that the inverse mapping applied to X as an element of R is just going to be X times this base vector 1, 2. Okay. Clearly, this inverse mapping is the inverse of this mapping, because if I take F of T 2T, I get T, and if I take F inverse of T, I'm going to get T 2T back again. And the lemma that we just showed establishes that F inverse is also an isomorphism. So we have an isomorphism. F inverse goes from R to L. All right, now we're going to show that isomorphism is an equivalence relation between vector spaces. All right, and this will be important because this will help us to characterize vector spaces in a very convenient way. Okay. Now remember what we've shown about equivalence relations. The definition of equivalence relation is a relation that's symmetric, reflexive, and transitive. Okay. So we're talking about relation between vector spaces. So we're saying that the relation is that V is isomorphic to W. Okay. We want to show that the three things. What does symmetric mean? Symmetric means that V is isomorphic to W implies that W is isomorphic to V. Reflexive means that V is isomorphic to V. Transitive means that V is isomorphic to W, and W is isomorphic to U, implies V is isomorphic to U. So let's prove these three things one by one. We'll start with reflexivity. Reflexivity means that any vector space is isomorphic to itself. So what that means is that we need to exhibit a mapping that's one-to-one onto and also preserves operations. All right, now there's a clear candidate for a mapping that's one-to-one onto and preserves operations is the identity map. The identity map maps every vector in V to itself. All right, id V takes V to V, and id V operating on vector V is equal to vector V. Okay. Now this mapping id V is one-to-one because only one vector maps to itself, and it's onto because every vector has itself to map to it. Okay. And if you want to show that id V preserves linear combinations, you just take the identity operating on a linear combination, and that's just the linear combination itself. But each vector is identified with id V, and we get the structure-preserving equation that we need. Okay, so the upshot is that any vector space is isomorphic to itself via the identity map. Let's move on to symmetric. Okay. All right, if V is isomorphic to W, then W is isomorphic to V. Well, this is what we just showed, that if we have an isomorphism, then the inverse map is also an isomorphism. So that establishes the symmetric property. The transitive property, if V is isomorphic to W and W is isomorphic to U, then V is isomorphic to U. So what we're going to do is use the transitivity of bijections. Let F be a function from V to W that's an isomorphism. Let G be a function from W to U that's an isomorphism. And consider their composition. Composition means that you apply F first and then G. Okay, so we draw the picture here at V, W, U. F takes V to W, G takes W to U, and G composed F. We write G composed F because you apply F first and then G. G composed F will take the original space V to the final space U. Okay. All right, now here he's using the fact that the composition of bijections is a bijection. That's another fact that you can check from your discrete math textbook or your abstract algebra textbook. Okay, so we only need to check that composition preserves the linear combinations. And this is just repeated application of the linear combination principle. G composed F, acting on a linear combination, is G of F of that linear combination. Then we apply the linear combination principle to F of this linear combination to break it up into two parts. Then we can apply the linear composition principle to G because G is acting on the linear combination of these two vectors. And then here we simply use the fact that G of F of V is the same as G composed F operating on V. All right, so we have the statement that we need, that G composed F operating on a linear combination is the same linear combination operating on G composed F of the constituent vectors. Okay, so this result tells us that the collection of all finite dimensional vector spaces is partitioned into classes. Two spaces are in the same class if they're isomorphic. Well, we talked about this before, that if you have equivalence classes, then any element that is related by this relation can be grouped into a single class. Okay. Now this next result characterizes these classes. We will find a characteristic element in each one of these classes. And we know that any other vector space in this class will be isomorphic to this characteristic element. Okay. All right, now, so here's our ultimate theorem. Vector spaces are isomorphic if and only if they have the same dimension. The proof is in the next two lemmas. Let's go on and see how that works. Okay, if spaces are isomorphic, then they do have the same dimension. Okay, so we're going to use the properties of isomorphism to show that any two isomorphic spaces have the same dimension. Okay. So, to prove this, we will show that an isomorphism of two spaces gives a correspondence between their bases. Okay, now remember, isomorphism takes every vector in one vector space to a vector in the other vector space. So in particular, it will take a basis in the domain to a set of vectors in the codomain. And what we want to show is that that set of vectors in the codomain is also a basis. Okay, we shall show that if f from v to w is an isomorphism and a basis for the domain v is beta 1 through beta n, then the image of this basis b, which is d, consisting of f of beta 1 through f of beta n, is also a basis for the codomain. Okay, so here you have your vector space, and you've got a basis here. This is v with the basis here. Now, these three vectors, when they map to w, they can map to three vectors in three other directions, but the point is, the idea is that if this is a basis over here, then these three vectors here are also a basis in the codomain. Okay. All right. Now, the other half of the correspondence, that for any basis of w, the inverse image is a basis for v, follows from the fact that f inverse is an isomorphism, and we can apply the same sentence to f inverse. Okay, so any basis over here will map via isomorphism to a basis over here, and any basis over here is the image of a basis over here. So let's get down to proving that. I remember that B is a basis. Is a basis of V. And we're saying that D is equal to f of beta 1 through f of beta n. Okay, and we want to show that D is a basis of W. Okay. First of all, let's show that D spans W. Take any vector W in W, and we want to show that any vector W in the vector space W is a linear combination of these vectors in D. Okay. Because f is an isomorphism, f is onto. So there's a vector V in the original vector space V such that this fixed W is the image of V. All right, now we're working in the vector space V. We can expand this vector little v as a linear combination of basis vectors. Okay, so this little vector V is a linear combination of basis vectors. Now, since W is f of V, then W is going to be f of this linear combination of basis vectors. But then I can use the isomorphism properties to show that f of a linear combination is the linear combination of the f's. So I can pull out the constants. I can write the f separately. And notice that f of b1, beta 1, that's in D. F of beta n, that's in D. So in fact, W is spanned by D. So this means that W is in the span of D. Okay, I've written f as a linear combination of vectors in D. Now, let me show the remaining part to show that D is a basis. We need to show also that it's linearly independent. Okay, Suppose that we do have a linear relation between the vectors in D. So we have a homogeneous relation where we have a linear combination of vectors in D and get a zero. Okay. Now I can write this linear combination using the isomorphism properties as f of linear combination of the betas. Okay. Now, since f is 1 to 1, the only vector that is sent to the zero vector in W is the zero vector in V. What does that mean? In order to have 0 equal to f of something, then this thing inside must also be 0. This must be 0 in the vector space V. Okay? If this is 0 in the vector space V, we have 0 equals a linear combination of basis vectors. The only way that can happen is if all the C's are 0. Okay? So the upshot is that if we have a linear relation, if we have a homogeneous relation relating the vectors in D, we can also find the same homogeneous relation relating the vectors in B. But since B is a basis, the only possible relation, the only possible linear combination that gives 0 is the combination where all the coefficients are 0. So that means that the original combination of vectors in D must also have coefficients equal to 0. So we're playing off the identification of vectors in W with vectors in V. Okay, so that completes the proof that the vectors in D both span the vector space W and are linearly independent. That implies that D is a basis of W. Okay. All right. Now, so what we've shown is that if two spaces are isomorphic, then they have bases with the same number of vectors. So in other words, they have the same dimension. Let's show this the other way, that show if two spaces have the same dimension, then they're isomorphic. And that will complete the identification of dimension with isomorphism. Okay. All right, so we will prove that any space of dimension n is isomorphic to Rn. All right, so remember our equivalence class picture. We've divided vector spaces into equivalence classes. And of course, Rn is a vector space. And what this theorem shows is that every one of these equivalence classes has one Rn in it. And as long as the vector space has dimension n, it's going to be in the same equivalence class. Okay, so one equivalence class would be characterized by R1, and all one-dimensional vector spaces are isomorphic to R1. Another equivalence class would be the class containing R2, and all two-dimensional vector spaces are isomorphic to R2, and so on. Okay, so once we get that every vector space of dimension 2 is isomorphic to R2, that means that every vector space of dimension 2 must be in the same equivalence class with R2. So R2 is a characteristic element of that equivalence class. Okay. All right, now suppose we have an n-dimensional vector space, and let's fix a basis. Now let's define isomorphism in the following way. Any vector v in this n-dimensional vector space can be written as a linear combination of vectors, of basis vectors. And we're going to identify this linear combination of basis vectors with the coefficients in the representation. We also called these the coordinates in earlier discussion. So we can clearly map any linear combination of basis vectors into its coordinate entries. And we'll call this mapping rep B. By the way, I should mention that this is a function. This is a well-defined function. Because we showed already, I don't know the exact reference, but you can look back and find it, that every V in V has a unique representation as a linear combination of the basis vectors. And that's necessary in order to guarantee that this function is well defined. Because suppose a vector in V had two different representations, well, we wouldn't know which representation to choose. But in fact, since there's only one representation, there's only one way of associating every vector V in the vector space with a set of coordinates. Okay. Now, if you go back here, you'll find that this is exactly what we did in this linear mapping here. That in fact, see, if you had a vector in L was t times 1, 2, well, 1, 2 is the basis, and we mapped t times 1, 2 to the number t. So you're actually mapping the element of L to its coordinate expressed as a linear combination of the basis vector. Okay, so this is a special case of the mapping that we're now doing in general. Okay, all right, so let's go here. All right, so first of all, let's show that this mapping satisfies all the properties of isomorphism. Okay, so the function is one-to-one because if you have if you have two different vectors, or let's just say two vectors that have the same image under rep B, well, rep B of this vector is what? It's simply the coordinates, u1 through un. Rep B of this vector is what? It's simply the coordinates, v1 through vn. Right? Now, if rep B of this vector is equal to rep B of this vector, that means that these coefficients, u1 through un, must be equal to the corresponding coefficients, v1 through vn. And that means that, in fact, the two vectors themselves must be equal. So here we have one-to-one. Next, we're going to show onto, and well, what that means is we'll have to show that if we have any coordinate vector, we can find a vector in the vector space that has that coordinate vector, and that's very direct proof. If I take any coordinate vector of this form, w1 to wn, well, consider the vector in vector space V that is the corresponding linear combination of basis vectors. Clearly, this vector, w1b1 plus dot 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 plus wn(bn) will map to this vector here, w1 up to wn. So that means that w is in the image of rep B, which implies that rep B is an onto mapping. Okay, so we've got rep B is one-to-one and onto. Now we just need to show that rep B preserves linear combination. So we'll go ahead and do that. Rep B of this linear combination of vectors, well, we can write out u and v in terms of basis vectors. So I'm writing u as u1b1 plus dot 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 un(bn), and I'm writing v as v1b1 plus dot 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 vn(bn). So I can, doing algebraic manipulation, I can revise this expression into an expression like this. Now, rep B of this linear combination of basis vectors is simply the coefficients of the linear combination. And I can break this vector apart into its constituent parts. This first vector is the coordinate vector for u. This second vector is the coordinate vector for v. So I've gotten that rep B of the linear combination of vectors is the linear combination of rep B of the individual vectors. Okay? So we have that any n-dimensional space is isomorphic to Rn. So we have, if V is n-dimensional, that's isomorphic to Rn. And if I have W is n-dimensional, it's isomorphic to Rn. Right. And because of the transitive property, that means that V n-dimensional is isomorphic to W n-dimensional for any two n-dimensional vector spaces. Okay, the second paragraph's representation map rep B is a well-defined function, since for each basis, each vector B has a unique representation with respect to that basis. Okay, that's the point I made earlier before the proof, that in fact we do have a well-defined function. Okay, so let's do an example. This plane, this is a homogeneous equation here, so it determines a subspace of R3. We've shown that this plane is closed under linear combination. We can parameterize this plane in the following way. You can treat this as, you can treat your y and z as free variables and write the solution set for this linear system, and this is what you come up with. This gives me a basis that spans the subspace, which is this plane. Okay, the basis has two elements, it's two-dimensional. So this plane is isomorphic to R2. As far as vector space is concerned, this plane is the same as R2. Although it's in 3 space and it's tilted, it's still, to all intents and purposes, the same as our usual flat plane, the xy plane. The corollary, a finite dimensional vector space is isomorphic to one and only one of the Rn. Okay, because a finite dimensional vector space has dimension n, and if it has dimension n, it's isomorphic to Rn. And we know that Rn is not isomorphic to Rm if m is not equal to n. So here's a picture clearly showing the arrangement of equivalence classes, and each equivalence class has a representative element that is one of the Rn's. And that, my friends, is it.